Okay, so here we have another polynomial division problem. We want to divide 2x cubed plus 5x squared plus 2x plus 22 by x plus 3. And again, we're going to set this up as a multiplication problem, right? We're going to set it up what we call the division statement, which is actually kind of a multiplication statement. We are going to write the dividend, the thing that we're dividing by the other thing. So this is the dividend polynomial, 2x cubed plus 5x squared plus 2x plus 22. We are going to write this as x plus 3, the divisor, x plus 3 with maybe a better looking 3 there, times the quotient polynomial, q of x. This is going to be a quadratic polynomial because we're multiplying it by a linear polynomial, degree 1, and we're getting a cubic. So the degree of this, 3, is going to be the degree of this one times the degree of that one, because you add the degrees when you multiply polynomials. And then we're going to have a remainder, and the remainder has to be a constant because the divisor is linear and it has to have a lower degree. And we talk about the reason for that in other videos. But here we're just going to do the division. And by the way, if you're thinking, how is this a division statement? Well, remember, we can write 7 over 2 as 3 plus a half, 3 plus 1 over 2. Or we can multiply through by 2 and we can get 7 is 2 times 3 plus 2 times 1 over 2. Or in the way that we're doing this, we can write this as 2 times 3 plus 1. So we can write the dividend as the divisor times the quotient plus the remainder. So exact same way, right? Divisor times quotient plus remainder. And the remainder has to be smaller than the divisor. Why? If it were bigger than or equal to the divisor, we would just increase the quotient, right? If the remainder were 2, this would be 2 times 4. If the remainder were 3, this would be 2 times 3 plus 3. We could separate the 3 into a 2 plus 1, and then we increase it to 2 times 4 plus 1, right? So it always works out that the remainder is less than the divisor, and the sort of polynomial world analog of this is that the remainder has to be lower degree than the divisor. So after I said we'd do it in another video, which we talk about the idea behind this in other videos, but we got a brief explanation here. Okay, so let's do this again. Let's reverse engineer this quotient. Let's figure out what this quotient is. And again, it's going to figure itself out, right? We are going to have no choice about what we add to the quotient, what we put into the quotient in every position. So again, we look term by term. I'm just going to match the highest power term and then worry about the next one later. Then match that one, worry about the next one, etc. So I have an x here, and I ask myself, what do I have to multiply x by to get 2x cubed? Well, that's going to be 2x squared. I have to multiply x by 2x squared to get 2x cubed. And that is my leading term taken care of, right? That is this one taken care of. That one matches. But then, of course, you have to distribute it into both of the terms, right? It's going to multiply by everything in that left term there, that bracket there, the x plus 3. What's 2x squared times 3? That's 6x squared. So we get a 6x squared as the next thing. And then next, I look at the x squared terms. How many x squareds do we want? The x squared term is supposed to be 5x, right? 5x squared. Right now we have 6x squared. So to make it 5x squared, I need a negative x squared. We have to get a negative x squared to turn the 6x squared into a 5x squared. So now I ask myself, what's the next thing I put in here? It has to multiply by that x and become a negative x squared. So I'm going to put in a negative x. I'm pretty sure negative x is what you multiply x by to get negative x squared. And in fact, it is. So this gives me 5x squared. And if we want, we can sort of consolidate this at this point and say, all right, we have 2x cubed plus 5x squared so far. And this is stuff that we want, right? This is exactly what we want for those two terms. But the negative x here, again, this is not done. This multiplies by the 3 and gives us negative 3x, right? Negative x times 3 is negative 3x. And how many x's do we want? We want 2. So what do we have to add to negative 3 to get 2? It's going to have to be 5x, right? We're going to have to get plus 5x's here. So what do I put in there? Well, whatever I have to multiply by the x to get 5x's, I'm pretty sure that's 5, right? The last time I checked, it was 5 that we have to put in to multiply by x to give us 5x. And then we can consolidate this again. We can bring them all down and get 2x cubed. We'll have 2x cubed plus 5x squared plus 2x, right? This and now this matches. This one matches as well. So again, we're just doing one thing at a time, not worrying about the rest, confident that this thing is going to work out. And by work out, I don't mean it's going to be a factor. It won't necessarily be a factor. Not all polynomials are divisible by all other polynomials, but we might get a remainder, and then we're done, right? Then we have factored it. We have found the quotient and the remainder. That is the goal. So what's the last step? The 5 multiplies by the 3, and is this the same color I was using? Yeah, this is it. This is going to be plus 15. At plus 15, we wind up with plus 15. What is the constant that we're supposed to have? The constant term, and this color is not very visible. Let me do something slightly different. There we go. I think you can see that better. There we go. The constant is supposed to be 22. So at the end of this process, right, our output is 2x cubed plus 5x squared plus 2x plus 15. So if we multiply this stuff by that stuff, right, this thing by that thing, this is what we get, except my box is going away here. It's supposed to, we want it to be equal to that, right? If the left-hand side is going to be equal to the right-hand side, well, we had a 22 there, only a 15 here. So what is the remainder for? It's exactly this, right? We add 7. The remainder is going to be 7 because we can't extend the bracket. Notice each time, right, we go down by a power of x. This was 2x squared. Then we have the wrong number, and this gives us the right number of x cubes, wrong number of x squareds. So we put in an x. That fixes the number of x squareds, gives us the wrong number of x's. So we put in a constant. And the reason we go down a power every time is because multiplying it by that x, that power of 1, that increases the power. It increases the power of 2x squared to x cubed, increases the power of x, 2x squared, increases the power of the constant to make it an x term, a linear term from power 0 to power 1. We can't do that again. We've run out, right? We have gone down to the constant. If we put in anything else, and all of our other terms are fixed, right? These are correct. These are the number that we wanted. We put in something else that's going to screw those up, right? So that's why we have no choice. We put in the remainder is 7. And now we have our polynomial division statement. This thing on the left here, this 2x cubed plus 5x squared plus 2x plus 22, this is equal to x plus 3 times 2x squared minus x plus 5 plus 7. And you can check if you FOIL this out. So we have our quotient polynomial, q of x is equal to 2x squared minus x plus 5. And then our remainder polynomial, and this is just a constant, right? Remainder is equal to 7. And by the way, this is something, this is actually a theorem that we learn in other videos, but you can see from this, right? If this is the polynomial p of x, this is the polynomial p of x here. Well, what if I plugged in x is equal to -3? What if I plugged in the root of x plus 3 here? We would get p of -3 is -3 plus 3 times 2 times -3 squared minus -3. I don't really care about this part of it because this one is 0, right? So I'd get 0 times all this stuff, so I don't need to compute that because the whole thing is going to become 0 when you multiply by 0. And then plus 7, right? The only thing that would be left standing when we've canceled that because it's 0 is the 7. So we have p of -3 is equal to 7. This is the first one of these polynomial division videos where we've seen a remainder. Previously, it was a factor. This one we have a remainder. And this is actually something we talk about in another video as well. the remainder theorem, the remainder theorem, which says that the remainder of a polynomial p of x upon division, upon division by x minus a, and this is for a in the real numbers, is p of a. Right? We state this in generality in the other video, but you can see it, right? The second that you do a poly, and this is why I'm always encouraging people to get really, really comfortable with polynomial division, because it leads immediately to stuff like this, right? We can understand the remainder theorem. The first time I learned it seemed really mysterious, because we hadn't done polynomial division this way, right? Doing it, so presenting it in terms of, an algorithm that we don't really understand, or the division way of doing it, dividing everything through, right, and getting the quotient and then the remainder over the divisor, it just doesn't make it as clear. So seeing it this way in terms of division, in terms of multiplication, like we did up here, and again, this is a very mathematical way of viewing division. This is the sort of number theory way of viewing division is we have the quotient, we have the remainder, and we can write the division statement, which is in terms of multiplication, makes things like the remainder theorem very, very clear. And so, of course, I encourage everyone to watch the remainder theorem videos. But it basically just comes directly from the definition of, or from the process of polynomial division, the fact that we can write these division statements, and also the factor theorem, of course. The other things in our polynomial division toolkit, along with polynomial division like this, are the factor theorem and rational roots theorem. And we talk about those in other videos.